Okay. Let me see. Probably. Okay. So how do we make this big screen?
Full
Uh,
screen.
because if I download this, um,
Yeah, you go to this in the left hand side on the smiley face.
left hand side is my
Yeah,
face.
the icon on the smiley face where the folders are. No, down in your computer, not here. In your
Okay.
computer. Yeah, on the
Yeah.
left side. Yeah. And then
Do you see it now?
yeah, yes,
Awesome.
exactly. Perfect.
Amazing.
Okay. Sorry for that. Okay.
No, it's okay.
Okay. So shall I take it away?
Yes,
Yes.
please go
All
ahead.
right. Yeah. No. Thank you very much for the invite, and I really appreciate the efforts in the ICTV side to do this. I have also participated in the one in Sudan. That was probably like 1 month or so ago. I'm very excited to share with you some of the science I have been doing and just broad picture here. If you have any questions, you can send it to the chat or you can just unmute. Um, I will try to talk, somehow more basic and engaging level. But if you have more questions, you can always send me email or connect over LinkedIn. Um, so let's get started here. Um, so I work in astrophysics and astronomy, and I want to show this image, right? So this image basically one of the most beautiful images that have been um, pictured by James Webb Telescope, which was launched um, about 2 years ago now. So this is a big image, right? It has so many galaxies. Every dot here is basically a galaxy, and as you see, that galaxies becoming different colors and different shapes. Um, and different locations and environment, right? So the question here is that how do we really extract all this information from here, right? Like we have basically rich information here. So how do we get that, right? And most of the traditional methods that I will describe in a bit, for some of it in a bit, it's very hard actually to do this because we are coming to a very big, large scale and big data, and we need to have different methods and tools to be able to extract information from these large scale, beautiful data sets. Um, so this is why do we need machine learning here? This is basically the timeline for experiments by NASA and other major facilities. Um, we have this timeline for the surveys. Um, it's an exciting time. We have the recent launch of JWST, which is James Webb Space Telescope, which has an extremely high resolution, which is able to detect most of the faint galaxies and the faraway galaxies. Um, we have we are expecting the launch of Roman Space Telescope coming up next year, um, and so on. And we are waiting for the square kilometer array and all other arrays here. So most of this timeline of these surveys, they share one thing. They're all coming to uh, probe large scale universe to see all this distribution of galaxies and the beautiful structure we have in the world. And and they will provide big data, large scale. It's an extremely large data set and it's extremely massive. And that's why most of the traditional methods is very hard to use to extract most of the information. That's why we need a new set of tools, which basically um, we are very lucky to see the development of machine learning to be able to use these tools. Um, so in general, what is machine learning? I know you have been talking about this for the past 2 days, but just in general, basic introduction here. If we have a machine, right, and we want to teach the machine how to classify or identify between dog, cats, and dogs, right? You could actually program this explicitly in the computer, and you could describe every single feature, what the cat looks like, what the dog like looks like. and then you can actually write it in a program within the machine, and then the machine can follow that. But what machine learning does is that it's basically you show lots of data, right? You just show all the possible different data and images of cats and the images of dogs, and then let the machine figure out, try to understand all these different features and stuff. So basically, it's a way we are not explicitly programming what we need, but we show lots of data, and then we let the machine learn the different features by itself, and that's why it's a very exciting field. In the same way, in astrophysics, depending on the problem we want, we can just show lots of galaxies, right? Like if we want to classify between them, we can just show lots of galaxies, we can show lots of maps, and let the machine figure out the features and the things that we are interested in. Okay, so it's exactly the same process in data science or in computer science. We do the same scale where you have just to think about the data you want and you generate them, and then depending on the task, you ask the machine to learn that task. So let me explain to you one of the traditional methods we used to have, and I show you to prove why machine learning is really interesting here. So usually, let's look at this example. You have two different fields, right? You have completely two different fields, right? Like you look at this field. These are, we call them density field, which is basically the same as the map for galaxies you have seen, but it's only just showing the density, right? Like each dot here would be like over dense regions that might be able to form stars and structure in galaxies, but these are completely different fields. So this is one simulation, think the universe look like that. The other simulations look, this universe is like that, but they are completely visually different, right? But because in the past we didn't have lots of memory and computational power, right? It's very hard to process this image because the image is large. And let's say if it has 100 pixels, or like this is 250 pixels on each side, right? If you multiply 250 by 250, that's really huge, right? Like you have over probably 10,000 pixels in this image. And it gets very hard to process that if you don't have a really powerful computer. So what we tend to do in the past, let's just summarize this image. Let's do data compression. Okay. So in the data compression, you basically try to find what would be the best descriptor to this field. And maybe let's just try to summarize each one of these fields in 10 points or 20 points. So one way you can think about it, maybe I can do histogram, right? Like you can take this image, right? And you can just flatten the image, and then you can just compute what is the counting, right? Like the histogram, the probability density function for these fields. One of the other things we do is just something we call the power spectrum, which is basically you take this image, you move it to the Fourier space, right? You make Fourier space transform, and then you take the average of that image in the Fourier space. So, and the power spectrum, one of the interesting things because it captures many details in these images. But the most important thing here is that if you look at these two completely different fields, but when you compute their power spectrum, which is the blue and the red, they look exactly the same, which means we are basically losing information. When we do this, we lose it because this power spectrum, if we use it, we cannot really differentiate whether this power spectrum coming from this field or that field. So because they are the same, and you lose lots of information for that when you do data compression. And therefore, we need to work directly with these large scale maps. Okay, so and that the way that you can work directly with them without doing any compression is using machine learning. So I will talk mainly about most of the machine learning models. They have two main branches. There are two main branches in machine learning models, and they all come from this equation, or they are modeled through this equation. And this equation basically it's Bayesian statistics equation. It's a famous one. You don't have to know the deep details of it, but you need to know something we call posterior distribution and likelihood. And basically, this is what we model, right, in most of the statistics and analysis. the posterior distribution is basically just the probability of the model given the data, right? Like you have data and you have lots of models, right? And then you want to know which model really fits the data. So that gives you the posterior distribution. And the likelihood is basically given lots of data you have and you have a single model, like what would be the model that fits the data. So it's a different way to think about modeling things. So the posterior distribution of the likelihood, and machine learning models that aim to model the posterior distribution directly. These, we call them discriminative models. And the models that they are actually models that the actual likelihood, right? That they try to find the probability of the data, so they generate more data. They call them generative. Here they are discriminative because you are trying to find the model. So these are discriminative models, a discriminative way. And the generative is you are trying to generate data out of the model, right? And that's why we call it a likelihood, right? And the current direction more in the machine learning direction, people more, as we know that we have in the revolution of generative AI. So most of the current attempts and people push more towards the generative models because they are more probabilistic and discriminative somehow. Mostly they are more like deterministic approaches. So I will try to highlight some of the work that we have done in different directions for discriminative way and generative way. And hopefully if there is time, I can talk a little bit about large language models and their possible use in astrophysics. Okay, so this is one example where we can, in the discriminative model, where we try to model the posterior directly, where we have this question, right? So we have one map of the universe, right? So this is map of the universe. What it shows here, it's a simulating map from the simulations, which shows we have a time in the universe in the past where we call it the epoch of reionization. And this epoch of reionization, it's the time when galaxies started to form and they started to emit light, and that light went into the gas in the universe. So the universe was fully gas before any formation of structure, right? After the Big Bang. And then everything was gas. And then the gas was neutral, basically. And then galaxies emerged and came up. And that's also debate the structure formation and other things. But anyway, most of the luminous sources started to come up. And they started to emit light, and the light started to ionize the gas. So this is a very important period for us. We need to understand it. It's responsible for many directions here. So it's a very important thing. And there is a debate in the field whether these ionization, you see all these black bubbles, these are black bubbles coming from some ionization sources, right? So you imagine any black dots here, there is a galaxy behind that tries to ionize this region. And there is a debate whether this ionization of the universe happens through galaxies, right, or AGN. AGN, basically what we call them active galactic nuclei. And these are black holes that they are active, right? And when they are active, they emit much stronger light than galaxies would. So then the debate is that whether we do this. So then one of the goals of the upcoming experiment is to provide images for this ionization. Then from our theory, we are responsible to try to find out whether this is happening through galaxies or radiant. And this is where machine learning comes in. You can basically design one of the most famous architecture, which is called convolution and neural networks, where you try to passing, right, the image and you convolve it, right, in a series of neural networks, right, that is able to, and the purpose of the training, right, is to be able to find what are the optimal filters and the optimal kernels and the set of neurons, right, and the set of weights that you can use in this network in order to maximize the prediction, right? So the maximizing the prediction either you get 0 galaxies or 0 ADA. Of course, you have to run lots of them. And then you have to monitor your training. And unfortunately, in machine learning, most of the architecture, they cannot learn everything by one epoch. So you need to run it through different epochs, which is what we call like the training steps, which is you go through the data many times. And as you see here down here for what you see here in the x axis, the training steps, y axis, the accuracy, and as a function of the training step, you see for different times in the universe, we were able to get a very high accuracy very quickly, right, from a few training steps. This is one of the applications that is really successful. Again, you have to think about the problem, you have to generate lots of data, but it's very successful and it works, okay? In some cases, it doesn't work because when the universe is fully ionized, you have only black map, dark map, you can't really tell which one it is. But if you have still a bit of structure, that can be good hints, you know. Anyway, so that's just one of the successful application. Another successful application also is that in the first one, we tried to classify the sources, whether this ionization of the universe happened through galaxies or radiant. Here we have another problem, right? This work has been done by Comello. He's used to be my master's student, but now he's in the SKA office in South Africa. And this work we're trying to find also in the discriminative way, right? Because we're trying to find out what is the probability, what is the probability of the neutral hydrogen, which is basically the average neutral fraction in this image, as a function of this image, right? So that's you trying to extract physical labels from data set. That's usually a discriminative way, targeting the posterior distribution directly. And you might think, you know what, yes, that if you have an image, you can take the average of it. Why do we need machine learning here? We need machine learning because we know that systematics and noise from the telescopes, they contaminate our signal. So what you see in the left-hand side, these are examples of signals, simulated images coming from the simulation, right? But when you try to observe them, you can say, oh, this is my simulated image, but how would this experiment see it, right? Then you have to add the noise from the experiment, right? You have to add all the different sources of contamination from the sky, from the ionosphere, from the experiment itself, thermal noise, many complicated systematics. And when you add these systematics, you can come up with the images on the right-hand side, which we call them, these are mock images, as they would be seen by square kilometer array. And of course, when you add all these systematics, the image changes, right? And there is no guarantee that the average of the image by the left-hand side is the same as the average of the image in the right-hand side. And that's why maybe with machine learning, we would be able to learn this much quicker. And again, what you can do is that you can design a similar architecture to what we have seen, where you pass your image through a series of neural networks, and you try to compress the image as you go along these networks, and then you try to predict at the end what would be the neutral fraction for these images. And then at the end of the day, we see that with a very simple neural network, we were able to predict. What you see here is that y-axis is the prediction from the model, x-axis is the target value, which is coming from the training set, what we train the model to learn. And as you see, if we train with the simulated set or the mock set, data set exactly, we are able to recover, this is like the perfect line, right? Which is the unity line. If the model is really able to predict everything, it should follow this diagonal line very, very nicely. So these are examples in astrophysics, which we target extracting information directly. There are different other architecture at the top. But at the end of the day, you just generate lots of data, you design your target, right? Your scientific question, which takes lots of thinking. And then once you have that scientific question, you start to generate lots of data and you start to train and you pick up the right model. So that's in the discriminative side. Let's look at the generative side because it's, I think, more exciting, more interesting, and it captures much more of the details, right? And one of the nice things you think about it in the statistic is that if you have the likelihood, you can recover the posterior distribution, right? Because the posterior is equal to the likelihood times the probability, which is something we call like the prior of the model. But if you are modeling the posterior, it's very hard to capture or to recover the likelihood. So this is one of the things that's why we will more into the direction of the likelihood here. So I will talk about this again. I just tried to make the scenario for all this ionization. So then we have one story to talk about in different application. So this is also work because it's done by Mosima. She's a PhD student in South Africa too. And how do we do this generative models, right? So let's talk about simulation, right? Like how do we do the simulation, right? Most of the simulations in the fields, they are extremely complicated and very expensive. They are very slow and very expensive. What we do is that for us to arrive to the ionization field in the right, we have to go through many, many steps. And the first step, we have to generate the density field because everything is coming from gas, as we said. So you have to generate the density. Then after you generate the density field, then you have to think about your sources, what the sources would be, whether they are galaxies or active galactic nuclei, and how do you even model the galaxies, right? The light out of galaxies. So you need to think about many processes along the time of the evolution of the universe, which is extremely complicated, and that it takes time. So for running one simulation, depending on how big the box of the simulation is and the resolution and the details and how sophisticated you want it your model and how accurate your model you want it to be, this actually could go anyway from 1 day to 1 year. One of the most expensive simulations we have in the field, that they capture very small gas particles in the universe up to extremely large galaxies. They could run for 1 year in a big super facilities, computing facilities. So they are extremely expensive. So how do we, but then it's very hard if we want to train our models. And if we want to extract information, we need to generate lots of data. And if we want to generate lots of data, we can't really do this. And we wait 1 year for 1,000 images, and then we wait another year for another 1,000 images. It's very hard to do so. So what we can do is just try to learn this, right? So we try to find models that they are approximated. They are a bit faster to generate training data set, which is one of these models. And then we try to go from the density field to the ionization field to generate our training data set. And the question now we ask is that, given the density field, can we generate the ionization map quickly? We don't have to go through the sources in the middle. We don't have to go through anything, just directly from the density field to the ionization field. And if we are able to do this, generating the density field is very easy. You can just generate any density field, and then we can pass it through the model, and the model would be able to tell us what would be the ionization field. And if we are able to do this, we are somehow emulating the radiative transfer process, because if you want to get the ionization field from the source field, you have to follow the direction of the photons and where they go and where do they ionize and which cell they end up being ionizing or not. It's a very complicated process and very difficult process. So if we are able to go directly skip all this, then we are able to emulate this. So that was the purpose of this paper, which was accepted to the ICLR, one of the most prestigious conferences in machine learning. And one of the techniques you can do this is that one of the architecture for generating images is basically something we call a unit, because it has a U shape, right? And in this unit, basically, you're trying to go through series of convolutional neural networks, but then you go in a direction of this unit where you try to compress the information slowly, and then you try to recover them again. And then you can have some connection in the middle to add the remaining, to add the input images. These are just technical details, but this is the architecture, how it looks like. And you could try to model this in two different ways. One way is to just plug the map directly. The other way is to say, you know what, I will plug in the map, but I will add noise to the map, and then you can see there are different techniques how to do this, but I just wanted to show the different architecture here. And then you train with this. So you generate lots of maps, you generate lots of noises, and then just you try to predict what the ionization map is. And then during the testing, here is how the generation happens, because you are adding noise to your images, right? Then you basically, this is why we call it denoising. Denoising, this is not denoting, this should be denoising, where you start with your density field and then you add the noise. And then as you go through steps in the model, in the next generation, you start to see the ionization field growing, and then you stop when you need the right level of ionization in your maps. So this is a way that we call it denoising, because you are trying to learn how to get structure out of a noise. And this is what we try to learn, right? And if we want to compare whether our model works like model 1 or 2, we can take the density field. The ionization field here is the target ionization field we want. This is the prediction from model 1, which we don't add noise at all. And the other one, model 2, when we add the noise, right? And then you can compare their power spectrum. If you remember, the power spectrum is we take the image to the Fourier space, and then you try to compare them. This is one of the metrics you can use to tell whether the two models, at least at the level of the power spectrum, are comparable. And then what you see here, they are really model 2 gets much closer to the model the red one, which is the target, and model 1 is underestimating our power spectrum on these scales. So this is just one way to say that we are successfully here able to emulate radiative transfer process by just generating lots of images, lots of images, and we have a model now. People do not have to wait for a year or to generate large scale ionization maps. They can just use the model directly, and they can get this, in a matter of seconds, which is a huge speed gain. So this, I started with units because I want to take you into different architectures for application of generative AI in astronomy, or even the field of computer vision. And units are really the basic core for something we call diffusion models. And diffusion models, you have to talk about them when you talk about image generation, because we care a lot about image generation, because most of the telescopes, they just observe the universe, and they give us distribution of galaxies and sources in a big map, right? That's all we have. So we need to be able to work with images, and diffusion models, they are very interesting set of models. But before I tell you what it is, let me try to convince you what they are. So that is one of the, usually in the machine learning community, whenever they do, there is a benchmark data set. You have to prove that your model works very well with that, right? And one of the famous benchmark data set, we call it CIFAR-10. And this CIFAR-10, it's a very tricky data set. It has an airplane, it has bird, it has a cat and deer and horse. If you have a model that is able to learn this data set very well, and there is also like CIFAR 20 and CIFAR whatever, like I think up to 200, whatever. So there are different CIFAR data set, but this is the smallest one. And then you want to show that your model really works very well here. So there is this interesting website called Papers with Code. I recommend, if you are a machine learning guy, or if you want to actually be a machine learning person, usually you can find lots of these benchmark data set and accuracies there. So you go there and you just type what is your task, machine learning task, image generation, estimating parameters, whatever, and then it tells you all the papers with their score. And if you look at this score, if you write image generation on CIFAR-10, you try to find out that the best model is diffusion model. The first 5 models, 3 out of them, they are diffusion models. And the first 10, they are different variants of diffusion models and different work with diffusion models. So diffusion models are really dominating the market. They have been recently in a conference, which is also one of the most biggest, big conferences for pattern recognition and computer vision. And it was all diffusion models. Diffusion models is very interesting technique. So when they are diffusion models, we don't care about the equations here much, but basically think about it this way. You start with the signal in the left, right? this image of a dog, right, in the left, and then you slowly add noise to it. You just add noise to it slowly, 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 till you get completely noisy, right? Like you are completely contaminated by noise, right? And then what you do, you try to remove, in the reverse process, you try to remove this noise slowly, 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 till you recover your image back, right? And if you are able to learn this reverse process, starting from complete noise, right? And then you are able to remove the noise and you recover your image. Then you basically have the generative model, which is a diffusion model, right? So it's an exciting model. And of course, you cannot add noise too quickly, right? If you add noise too quickly, then you can't learn it. But as long as you are adding in iterative steps, noise slowly, 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 you would be able to learn it, learn the reverse process to remove it in each step back. Um, and it's the only problem with these models, they are slow, but they provide you the high quality images and in the field, right? So we need data set for this. This is one of the most exciting data set in astronomy. It's called the CAMELS, which is cosmology and astrophysics or machine learning data sets. It takes most of the state of the art simulations. You run them, lots of simulation, lots of simulations, and then you get the data. And then this is just to show you different realization of the data for, I don't know why this is doesn't, it should supposed to be a movie. But anyway, this shows you different architecture of the different realization of the simulation. This is for dark matter density. And then you can pick up any simulation you want. So you can go to this website if you want to play with any astrophysics and cosmology data sets. You can just grab this, easy to get, available publicly to use. So here is one of the examples. We also want to, for these generative models using these diffusion models, is that can we generate maps from parameters? So this is two parameters that we care about a lot in cosmology. One of them is called omega matter, which is basically how much matter should we have in the universe, or how much matter the universe has. And the other one is sigma 8, which is just like the amplitude for the fluctuations in the universe. So these two are very important. And when we run our simulation, we need to specify these parameters in the beginning. These are like hyper parameters. You have to specify, oh, I need the universe to have 0.3 or 0.8 or whatever. And then when you change these parameters, right, and you tune them, you can get a different realization of the map, right? So the question is that also these simulations are very expensive. They take month and month of running. Can we actually emulate this process, right? Can we use generative models that we need a model that just we give it these two parameters, it generates the map quickly. And we have done this with diffusion models, and this is just a comparison. What you see in the upper panels, these are the true images coming out of the simulation. On the lower panels, this is the diffusion model that we developed, and they look visually similar. It's very hard if I show you the first panel or the second panel, it's very hard to tell me which one is true, which one is fake. So this shows visually the power of the model itself. And if you are not convinced, you can go to the level of metric comparison, and then you can look at the PDF, which is just the histogram of these images, or you can look at their power spectrum that they have showed you, and at different parameter in the different range of the parameter space, like in different parameter in different region in the parameter space, we see that we are able to recover the correct VDF histogram of these images and the correct power spectrum of these images, right? So this is also a powerful way to do these generation. The other nice way to do generation, which is this is more for density estimation. It does give you nice looking images, but not as nice as the diffusion models, something we call normalizing flows, but they are powerful in other stuff, right? For estimating density, for other tasks, right? Like for estimating density, for something we call likelihood free inference. So before I tell you, also let me tell you what it does, right? So what you see in the left-hand side, these are human faces that are really generated by a normalizing flow model, right? You see the model, these are all fake faces, right? These are not true faces. They are not true humans, but you see the model is able to capture the small details like the dot in the eye. It captures the hair in the large scale picture, right? So it's a model, it has a very nice quality for capturing details, and they are extremely fast, and they don't need lots of data. They are not data hungry as diffusion model. So this is a very nice set of methods. The other thing that you can do with normalizing flow is something we call in the field likelihood free inference. Sometimes you hear it like simulation based inference. And what is this basically is that when you want to do analysis and estimating parameters, like coming up with these nice contours to tell you where is the broad range of models that they could satisfy some condition, whether fitting data or something. You need to assume the likelihood in most of the cases. People, if you don't know how to do it, the first assumption you make, okay, let me assume that the likelihood is Gaussian, or let me assume that it's a multivariate or whatever. So you always, when you want to drive these contours, you have to assume the form of the likelihood, and that usually bias the results, right? Because you don't know what the likelihood is, right? In many cases. And especially in astronomy, most of the signal we get, they are highly non-Gaussian. And therefore, it's very hard to know what are actually the likelihood. So instead of assuming it, let's learn it. So then you can generate lots of data. You learn the likelihood directly from the data set. And then once you have the likelihood directly, you can just generate these posterior distributions. And this is a nice code. You can look at it. It's called by Delphi. It's available in Python, of course. And they show here for estimating 6-dimensional parameter space. If you run an MCMC for that, you need at least 10 to the 6 realization, which is like at least a million. Million even is very small. Maybe like you need 10 to the 12 or something to capture all the noise in these models. If you run the MCMC, which is what is called Markov chain analysis, Monte Carlo Markov chain analysis, and then it takes a long time to run. But with this method, they show that you need only 1,000 simulations to estimate 6-dimensional parameter space, and they show that you are able to recover exactly the same posterior distribution. So it's a very powerful technique. So what it is, normalizing flows, basically, it's a way you think about it. It's a way that you convert simple distribution to complex distribution. And it's all happened with the change of variable point. Anything happens with that, right? So what you need is that you want to model what is the probability of X, and you need the inverse for that, right? So this happens only through this mapping, which is F. And the two conditions you need to satisfy in order to this equation to work is you need a mapping F that is differentiable, because you need to have the Jacobian for the change of the variable formula. And then you need a mapping that is invertible. That's it. If you are able to have these two, then you are able to model this mapping. And how do we do the mapping? The same. You start with the base density. It could be a Gaussian field. It could be anything. A density that we know very well, right? And then basically you apply a series of neural networks to skew this distribution to get your complex transformation or the transformed density you want, right? And then because this mapping is differentiable and invertible, right? If you go from the direction of the base density, once you know the mapping, right? Like once the mapping is learned through machine learning, then if you go from the direction of the base density to the transform density, you are generating new examples. That's why it's generative now. And also, if you go from the transform density back to the base density, you are doing inference. So the model is able to have this two. It's powerful because it has two this direction. That's why it's called flow, normalizing flows. And depending on the task you want, once you train this model, if you want to generate new samples, yes, let's generate. If you want to make it discriminative and find what is the posterior distribution, you can do so. And this is a work has been done by PhD student. He's Roy. He was visiting me in the States. And then we were doing the same exact exercise we had just now with the diffusion models, but now let's do it with the normalizing flows. And as you see, this is also, we show that we are able, given two parameters, two single parameters, the model is able to generate nice images for different values of the parameters, right? Like we have, this is the camels, which is the true training data set, and this is the generated maps from our images. And because the model is invertible, this is the extra thing we can do as compared to the diffusion model. Diffusion models, they can estimate likelihood, but these models, they are more flexible and faster to get this likelihood. And as you see now, we are able, what you see here, this is the posterior distribution. The red dot is the map that we want to recover. And then when you vary, and then you have the likelihood. So because you have the likelihood, you can do this in a second. This is one of the most exciting applications in astrophysics because it's very hard to generate this posterior distribution if you only have simulations, because the simulations are really, really expensive. And then people in the past, as I said, what they do, they take these large scale maps, they compress them into power spectrum or PDF in order to do so. So now we are able, because of the advancement of machine learning, we are able to estimate these parameters, have all this posterior distribution in a matter of seconds, without compressing information, without losing information, without waiting a month for simulations to run and do so. This is the exciting power of machine learning that we are able to. I will try in the rest, maybe like 5 minutes or so, talk about, of course, the evolution in large language model in astrophysics. I want to show you some of the attempts that they have been doing, and also the field have been doing different things. And we all have interacted with ChatGPT. We all have interacted with all these exciting models, Gemini, ChatGPT, image generation, and so on. And they are really transforming the way we do research. They are making things much more accessible and easy to process. And one of the applications you can think about of large language models in astrophysics is to have research assistant, right? What I show you here, right? This is the in the x-axis, the years. In the y-axis, the cumulative submissions, right? Like what is the number of new daily papers coming out as a function of the year, right? And these are for different fields like math, computer science, whatever, right? But let's look at astrophysics for instance, right? Which is AstroPH in the red, right? You see the red line as a function of the year, right? We are almost at 800,000, maybe more, maybe like around 1 million paper, right? So imagine you are a new student in the field and you are tasked to brainstorm ideas for projects, or you are trying to find the relevant literature, or you have some idea, but you want to find out whether this has been done or not, right? You want to know what is the relevant literature. It's very hard for you to go through 1 million pages, of course, right? And only people that have been in the field for a long time, right? Like professors that have been in the field from 90s or 80s, they would be able to know the literature much better than us. But even the professors, right? It's very hard for them because as you grow as a professor, also you have more responsibilities. It's very also hard to become very updated in the field. So you know the past, but less in the current time. And for the new students, they know more of the current time. They don't know the past. So you don't know everything, of course. So how can we do this, right? So this is something I tried to develop, which I call it Cosmogema. I provide links in the slide. You can go and play with it. And it's basically an AI research assistant. So how can we do this, right? We want to make sure that we are able to have some models, right? that are able to assist us in research and tell us many things, right? Um, but the problem with ChatGPT and all these models, they are not domain experts, right? So they are expert in general details because they have been trained in everything online, right? Um, so they are not really specified, right? So if you ask specific questions about cosmology or astrophysics or your own domain of expertise, um, you might not get the correct answer, or you might get a general answer, but not an expert answer. So if you want it to be expert answer, what we need is that we need to fine tune this model. We need to take these models and we try to fine tune them so they can adapt and they become more expert to this, right? So of course, machine learning always started with generation, data set generation. So what I have done, you go to archive. Archive has all the new daily papers. And then I made a nice experiment. I said, okay, let me try to select abstracts for papers came out from 2018 to 2022. And let me try to fine tune my model on that. And then after that, let me test on papers that came later, by 2023, and see whether the model is able to predict or to answer questions that came later in the field. So then, in order to have a research assistant that you can chat with, you need to generate question and answer pairs. And for the question and answer pairs, you can try to generate them from a model, right? Like you can take an abstract, you pass it through ChatGPT or Llama. In this work, I work with Llama, but you can use any other models. And then you can pass your abstract to the model, and then you ask the model, given this abstract, can you generate a question and answer? So then you can pass, and then you can generate your data set. So you need a question and answer pair. And then what I have done is that through all this about 3,500 abstracts, I passed them through a Llama model to generate all the question and answer pairs. And then after that, I took these question and answer pairs, right? And then I tried to fine tune one of the models called Gamma model, which is one of the open source models that Google has, right? And then I fine tuned them, and then I got about 95% of accuracy in the training samples, but about 75% in the testing sample. Actually, getting 75% is also really, really good because if you look at the bench, the accuracy for most of these models, sometimes they are 60, sometimes it's very hard to find model that's 90. It's very hard, or like 95 or whatever. So 70, 60, whatever, if you try to fine tune it in that domain, it's extremely interesting. And then after that, I deployed these models in one of the open source platform. If you want to learn machine learning, if you want to be engaged with the community in machine learning, most of the people and most of the nice, exciting discussions and models are happening in something called Hugging Face. So I encourage you to go to Hugging Face. It's one of the largest open source community for machine learning models. You go to Hugging Face, create your account. You can grab any model. You can play with anything. You can deploy stuff. You can see production codes. You can see application. You can get inspired by ideas for projects and for tasks. It's an extremely I highly recommend going into Hugging Face, and I deployed the model. So here I can show you a couple of the answers that the model has. So this is the model is deployed on Hugging Face platform. So the model is able to answer if I give it multiple choice answer. It gives me the correct answer. This multiple choice answer is coming actually from a set of from a curated set by astronomers as a benchmark data set, and it's able to get me the right answer. And then it also, what I found it extremely interesting, it can help me to brainstorm ideas for project. I'm interested in astrophysics, but I don't know what to do. I run out of ideas. Then I tell it, okay, can you just give me 3 ideas for interesting work to do it for advanced cosmology? And it gave me actually very sensible results, and actually told me things that I didn't know about. For instance, like I didn't know there is something called chronometers. And then I tried to look it up, and I realized, wow, that's a good way to estimate parameters and whatever. So it told me things actually I didn't know much. And yeah, so this is an exciting time. Um, here is the link for the codes in GitHub. You can go and see what I have done. I wrote a blog about it. And if you want to reproduce it, this is the link for the app directly if you want to go and interact with it. And I also added another thing called the Scheme Archive. I don't have time to talk about it, but it's also a large language model that is a large language model application uses large language models that is able to give you a nice summary of the daily papers coming out of archive every day. So you can go to Scheme, like rather than going to archive, you can just go to Scheme Archive. With one button, you would be able to generate summaries of the new articles very nicely. So with that, I will just give my summary. Generative AI methods were really transforming education and research worldwide. I would encourage you to learn more of the AI tools, apply them to your research and your life, and adapt to the evolution of AI because they are really, everything is evolving very, 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 very fast. And be careful, it can be really addictive. Let's connect. This is my email, this is my LinkedIn account. And I thank you very much for the invite and thank you for listening. Thank you.
Thank you very much, Sultan Hassan. It was really great talk. Guys, if you have any question, please unmute yourself or write in the chat. So we have one question from Laila. She's saying, does high accuracy on multiple choice questions truly reflect deep understanding in cosmology?
Yeah, right. I mean, it's a question. Thank you for the question. It's not about the specific field of the cosmology. It's more about how would you evaluate this? Evaluating large language models in extremely hard task, right? So how would you evaluate this? So one way you can evaluate this is to do yes and no, right? You generate yes and no answers, and then you say yes or no. That's fine. Another way you can do this is with multiple choice question, because now you can actually show the model. You can actually trick the model, right? Like you're tricking the model by showing the model different wrong answers, and you hide one correct answer in the middle. And then if the model is able to guess that, this is also a good way to test the model. Other ways that people test the model, which is also another direction, they call it, let's use LLM as a judge, which means that you take another large language models and then you show it the answers coming from the model that you worked on. And then you tell that large language models, okay, do you think this answer is correct or not? So there are lots of ways to do testing and evaluation. There is no correct answer, and you can get different answer by using different things. That's why it's an extremely like a big field of research now. So the more time you spend on evaluation and testing, the more you get maybe sensible results, and you evaluate the performance much better. But it's only one way to do this. That does not reflect at all that we have a very good understanding. But at least this is a data set for multiple choice questions that we know what the true answer is, right? And then if we are able, if the model is able to guess the right answer, while we show the model different wrong answers, or they are very close to each other, and then it picks the most correct answer, then maybe that's a way to test. But it's not a true reflection, because as I said, there are lots of ways to test. But that's a very good question, and it's an active field of research for how to test whether the model is really understanding the reasoning and the knowledge of the data set. But yeah, thank you for the question. That's a good one.
Okay. Here's another one. How does the unit architect capture both local and global features in radiation transport simulations?
Right. So for the units, where is the units? Let me see. Yeah. So the question is that how do they capture local and global? Yes. So these units, to capture the local features, what we in these units, basically they use convolutions, right? And this is one of the most important features in many of these architecture is to use convolutional neuter layers, right? And with the convolutional layers, you will have a kernel, and then you specify the kernel you want. It could be 3 by 3. Like if you have an image, let's say an input image 10 by 10, then you can have your kernel maybe 3 by 3. And this 3 by 3 would be able to capture as you train and as you scan, because it makes like a scanning to the image. This will help you to capture the local features. For the global features, as you see here, as you input the image, you see the image is really, we take the same image, we pass them through the unit, but at the same time also we kind of skip and add the image again to the output. This feature of skipping, what's called the skipping connection, it helps the training to become much more faster. And if you lose any information by going through the network, this way you can return the information. And this helps to retain most of the information in the image. So I would say by applying these convolutions that are within this network, like 16 or 32 or whatever, like these layers has this convolution, you can capture the local details. And this is one of the lessons that we knew from convolution and neural networks. And the other thing is that this skip connections helps you to retain all the features of the images and most of the global features. So yeah, so with these techniques, then this is how it could capture the features within the ionization maps.
Thank you very much. Are there any questions? If there is anything, you can unmute yourself. If not, then we thank again Sultan Hassan for his great talk and his generosity for giving a talk for Physics Without Frontier Afghanistan with collaboration of every.
Yeah, thank you very much. Thank you. This is really exciting. Thank you, ICTB, for all you do. And yeah, let's connect LinkedIn or in any over email. I'm happy to talk more. I also